Good afternoon, students. Today we are going to discuss about VH hysteresis measurement using an AC inductance method. In this, a given ferromagnetic sample is kept inside a primary coil, and then the secondary EMF, which is proportional to the dou phi by dou t, is measured. This will allow us to determine the magnetic properties of the given ferromagnetic material. And this experiment works on the Faraday's laws of induction, and because of the construction of the experiment involves a primary coil to set up the magnetic field and a secondary coil which is used to measure the induction that is produced by the magnetic field inside the magnetic material. This can be understood in terms of a transformer, a principle of transformer. The induced EMF is nothing but minus dou phi by dou t, where the which is can be related to the number of turns in the secondary coil, and A is the area of the coil, and dou v by dou t is the magnetic induction present in the material. And the circuit of the experiment can be shown in this fashion, where the input is taken from the line source, is given to a variac, which will allow us to reduce the 230 voltage to the required voltage, and further this from the voltage from the variac is given to a transformer, step down transformer, to reduce the voltage further, so that the current that is required to set up the given magnetic field can be controlled in a precise manner. Then the sample is kept inside the primary coil, which will experience the magnetic field. And the secondary coil, which is wound on the sample, will couple the magnetic induction that is present in the material, and that which we have seen from the previous slide is proportional to the dV by dt, is fed to an integrator which is made using an operational amplifier, and that integrator output, which is proportional to B, is now tapped across the integrator. The current which is fed to the primary to set up the magnetic field is passed through a resistor which is connected in series with the primary coil, in order to measure the current through the resistor, which will allow us to determine the strength of the applied magnetic field, which is also fed to the primary oscilloscope X plates. So the voltages that are measured between the X plates and the Y plates, which gives the applied magnetic field, as well as the B magnetic induction generated in the magnetic field, will allow us to measure the magnetic hysteresis loop that is present in the material. So we'll see the setup now that we are using in the experimental in the lab. So from the mains we are taking the voltage and we are feeding it to the rheostat, and the output of the rheostat is fed to the transformer, and the output of the transformer is now fed to the sample. And here I have to introduce you to a geometry which is used in this experimental setup. The geometry that we are using is called the toroid, and in this the sample is that we are using is iron silicide, which is casted in the form of a toroid, on which we wind a primary coil consisting of a thicker gauge copper wire, and we have chosen this thicker gauge copper wire precisely so that we can pass reasonably high current without burning the coil. And on the same toroid sample, we wind a secondary coil using a thinner gauge copper wire, so that the number of turns that are used in this gauge, in this coil, can be increased, which will increase the signal or the induced EMF, okay, thereby increasing the signal to noise ratio. So we use a thinner gauge copper wire to wind the secondary. So this is mounted on a platform, so that the step down transformer, the voltage coming from the step down transformer can be fed to the primary coil, and the induced EMF which is induced in the secondary coil due to the magnetic induction that is developed inside the material can be tapped across the secondary terminals. Okay. So these secondary terminals, as you can see, is now fed to a circuit which consists of an integrator, and you can see that you have an operational amplifier, and using a RC circuit that is shown in this diagram, okay, proportional to the one cycle of the input signal, we can measure the proportional integral output of the B. Okay, so this integral output from the op amp is now fed to the oscilloscope, Y plates. Okay, and similarly, the signal which is fed to the primary coil, the proportional to that, as I told you earlier, that we pass the same, we apply the same voltage to a constant resistor, 5 ohm resistor, in order to measure the current flowing through the primary coil, which can be measured using a multimeter, and the same is fed to the X plates of the oscilloscope. So you can see that there is a beautiful hysteresis loop that you can measure using this setup. And for energizing the op amp, we have a power supply, okay, 14 volts, 12 volts power supply, which can be used to energize the op amp, operational amplifiers. Then, you can actually control the input now, and you can control the input by reducing the voltage. You see that the loop area is shrinking. This loop is called the minor hysteresis loop. In fact, to measure the material properties, the iron silicide material properties that we want to measure, we should make sure that we need to apply sufficient voltage so that we measure the major hysteresis loop. The characteristic of a major hysteresis loop is that the loop gets saturated. That means to say that by further increasing the voltage through the primary, or by further increasing the magnetic field, there will not be any change or increase in the magnetic induction. The magnetic induction remains constant. So that is when we call that the loop is saturated. Now if you look at it, we can understand the hysteresis loop by looking at this curve, where we see that this point refers to the saturation magnetization or saturation induction in this case, where with increase in the field there is no increase in the magnetization value. So when we decrease the current now, and current when the magnetic field becomes zero, there will be a trapped or remnant magnetization that is present in the material, and that can be measured for a point where x is equal to 0 in the oscilloscope, which basically gives you the remnant magnetization. To decrease the remnant magnetization that is present in the material to 0, we have to decrease the current in the negative direction, and the point where the remnant magnetization goes to 0 for a negative field is called the coercivity or coercive field on the x-axis. Further increase in the field in the negative cycle will make the magnetization saturating in the negative field direction, and you see that the magnetization gets saturated again for a large enough negative field. And if we increase the magnetic field in the positive direction from this point, then again the loop traces back to the saturation value. So you see that the point where the remnant becomes 0, or the magnetization, trapped magnetization inside the material becomes 0, is called the coercive field, and the area under this curve is called the hysteresis loss or the energy stored in the material. Okay, so one can actually measure the various parameters. Once again, I tell you that the hysteresis, the saturation field, that is the field required to saturate the material, the saturation magnetization, the remanent magnetization, the coercive field, and the area under the loop. Okay, so using this oscilloscope, using the x and y scales that are given here, we can measure the loops, the different magnetic properties. This loop can be traced onto a graph sheet, and you can also measure the area under the loop, or if it is digitized, you can measure the area under the curve, which gives you the hysteresis loop. Okay, so we already discussed the mechanism or the responsible for the hysteresis loss in hysteresis that is observed in these materials. That is purely because of the domains that are present in the material. And you know that in the unmagnetized state, when there is no applied magnetic field, initially in the virgin state, all possible domain states are possible. That means the spins can orient along all easy axis of magnetization. Okay, thereby the net magnetization is 0. But when you apply the magnetic field along a particular direction, then the domain which is favorable along the applied magnetic field will start growing, and as the material becomes saturating, then the domains which are not oriented along the field direction will also rotate, so that the sample becomes saturating. And you see that the characteristic of the material, basically for a soft material, the hysteresis loop will be very, very sharp, in the sense that it is easy to magnetize the specimen and also easy to demagnetize the specimen. That means the coercive values will be very, very small. Whereas for a hard material like a hardened steel, you see that it will have a very finite coercive values. So that means the magnetization can be trapped up to a certain field. So we already discussed about the magnetization process. In the beginning, when H is equal to 0, the magnetization is oriented in all the equivalent directions that are possible or given by the magnetocrystalline anisotropy. And at low fields, depending on the direction of the magnetic field, the domains will grow in parallel to the magnetic field, and with increase in the field, the domains will try to rotate along the field direction, and at high fields the rotation is complete and the magnetization is said to be saturated. So the different parameters that are used in order to calculate in this experiment are: first we need to calculate what is the magnetic field that is applied, so that we can measure the saturation field or the coercive field depending on the value on the oscilloscope, the voltage of the hysteresis loop that is present at those points. So which is basically given by the NP into I, where N is the number of turns in the primary and I is the current through the primary coil. The current through the primary coil can be measured by the voltage across the resistor that we discussed some time back. And the resistor that we are using is a 5 ohm resistor, and if we know what is the current flowing through the resistor, we can estimate what is the current that is flowing through the primary. And you can see that, as I see that by changing the voltage value, you are able to change the value of the current flowing through the primary coil. And as I told you, we should ensure that we get a major hysteresis loop, so that the material is saturated. And so from the value of the multimeter, we can estimate what is the current flowing through the primary coil. And we know by the construction of the toroid circuit, we know that number of primary coils, number of turns in the primary, which is actually defined as the number of turns in the primary per unit length. So we know what is the length. That is basically length is basically given by for a toroid, it is nothing but a 2 pi r. So where r is equal to r1 plus r2, that is the inner radius plus outer radius. The average of that gives you r, and 2 pi r basically gives you the length of the primary. So we can actually calculate the number of turns in the primary. And in this experiment, we also look at another magnetic material, which is a ferrite. And for that, the geometry that we use is called a solenoid. And you see that this is a solenoid geometry. Again, this geometry is chosen precisely to decrease the demagnetizing factor to minimum or it will negligible value, because the length to the diameter ratio is such that the demagnetization factor for a solenoid for this geometry is negligible. And in this you see that the magnetic material is actually kept inside this primary on which the secondary is wound. You see that this is basically the magnetic material that I am talking about. This is a ferrite rod which is kept inside the primary on which the secondary is directly wound. Again, with for the same principle that the gauge that we used for the secondary coil is very thin gauge, whereas for the primary coil we use a thicker gauge wire to set up the magnetic field, which is sort of mounted again using on a board, wherein I can have a primary terminals coming to connect to the primary, and the secondary terminals the voltage is connected to the op amp to measure the B, magnetic induction. So except for that, the entire experimental setup would be the same. So we can actually use for this experiment what I showed you is a toroid, and we can use the appropriate magnetic units to measure the magnetic thing. And this experiment in fact can be done with different temperatures as well. As you can see that with increase in the temperature, the magnetic hysteresis loss, hysteresis loop or the magnetization will decrease. And so another important parameter that we need to measure, because if we want to measure the magnetic induction in the material, so the magnetic induction that we measure, basically Vy on the oscilloscope, is proportional to this quantity, which is basically given by, where K is the calibration constant of the integrator that we are using, Ns is the number of turns, A is the area of the coil, and B0 sin omega t is the magnetic induction. So in order to measure the magnetic induction, we need to measure the integration constant. So which can be measured by changing the input. So what we do is we basically measure by changing the input to the integrator. That means by changing the different by applying different magnetic fields, we can change the corresponding input to the integrator, and by measuring the output for different inputs, we can measure the integration, the calibration constant. So if you know the calibration constant and you know the number of turns and you know the area of the coil, and you can measure Vy from the oscilloscope, so I can actually calculate the magnetic induction for a given material. And if I measure this B at the saturation, I will get the saturation magnetic field, and if I measure B, that is Vy at x is equal to 0 or when the field is 0, then I get the corresponding remanent magnetization. So from this I can measure Br. Since I know the current flowing through the coil, I can estimate what is the coercive field value by measuring the Vx, corresponding Vx, and I can also measure what is the saturation magnetization, field required to saturation, saturation induction, and the hysteresis loss by measuring the area of the curve. So from this measurement, we will be able to calculate different magnetic properties which characterize the given magnetic material. And the corrections that are there in this experiment are, in principle, we should correct for the demagnetization factor to account for the actual field seen by the sample. But the two geometries that we have chosen in this experiment, namely the toroid and the solenoid, are in such a way that the demagnetization correction are negligible. So we don't need to really correct for the demagnetization factor. Coming back to the filling factor, which basically decides the flux linkage between the sample and the secondary, and to the applied magnetic field, which is also the primary. Okay, so that basically is given by the sample. We assume it to fill the volume of the secondary coil completely. In both these experiments, again, as I showed you in the case of toroid as well as in the case of ferrite rod, we are winding the coil directly onto the sample, thereby the secondary is directly wound on the sample, thereby the filling factor is equal to 1. The filling factor is given by the sample volume by the secondary volume, so which is close to 1. So this correction also, suppose if you are using a geometry in such a way that where the sample doesn't occupy completely full the coil, the secondary coil, then one has to take into account the filling factor. Okay, so this by this experiment we'll be able to measure the hysteresis loop, and you can see that if I use the setup for measuring for a solenoid, in which we are using a ferrite rod. Okay, a ferrite rod using the same experimental setup. When we measure BH loop experiment, we see that the hysteresis loop that we get will be completely different from the one which we have seen for the iron silicide sample. Okay, so this will enable us to characterize the given material, whether it is a soft ferromagnetic material or a hard magnetic material, and at the same time will allow us to measure the different magnetic properties such as saturation, remnant and the corrosive field values, which will allow us to choose the given magnetic material for a given application.